I will continue with the entropy chapter, and in the first lecture we have talked about the introduction to entropy and then the Cauchy's inequality, which was very important inequality, and it says that del Q by T, and it is either less than 0 or equal to 0. And if it is equal to 0, it is for that internally reversible processes. The internally reversible processes. And if this equality is less than 0, it means that it is irreversible. Okay. And for the internally reversible processes, we have said that you can replace this del Q by T, since this term is 0, and you can replace as a point function, and therefore del Q by T, instead of that one, you can write the cyclic integral of ds, and that one is equal to 0. But for irreversible process, we cannot do that one. And for today's chapter, for today's roadmap, I will first talk about the generation of entropy, which is very important and interesting subject. And then I will talk about the diagrams, entropy chains for incompressible substances as well as ideal gases for different cases here. And then non-conservation of entropy for different systems, isentropic processes, Bernoulli's equation, and isentropic efficiencies, and then what was entropy. Okay, so I will discuss the entropy at the end of the slides. Now let's start from the first one, entropy generation, which is the first roadmap here. So I have a process that goes from A to B in a reversible path, and it travels back from B to A in an irreversible path. This one should be irreversible. And I'm trying to understand what is the entropy change for this process. And I can write that del Q by T. This one is related to entropy, therefore I'm interested in this quantity for the A to B cycle. This is a cycle, and for that cycle, del Q by T will be equal to from A to B, that is del Q by T, plus from B to A, and that is del Q by T. And I know that for the A to B, that way, this one is irreversible. Okay, this part is irreversible. Let me use a different color here. This one is reversible, and this one is irreversible. Okay. For the reversible one, I can replace that term A to B with ds. Okay, and then it will be that s at b minus s at a. This is just a simple integral where you take the dx from, for example, that x1 to x2. That is equal to x2 minus x1. Similarly here, I'm integrating ds from a to b, and that one will be equal to sb minus sa. For the irreversible process, I cannot know it. This is unknown. And this general term, del Q by T, is equal or less than 0. Since this cycle is not perfectly reversible, totally reversible, it is not also irreversible. Okay, this cycle is mix of it. Therefore, it must be less than 0 as well as equal to 0. Because the equal to 0 is always for internally reversible process. This one is irreversible process, and for the cycle here, it is half reversible and half irreversible. Therefore, this quantity is less than or equal to 0. Okay, so with this one, for general terms here, this one and plus that one should be equal or less than 0. Now let's do that. I will write the relationships SB minus SA and the plus from B to A and del Q by T, and this term is equal or less than 0. Or I can write this one as this way. Let me do that. SA and minus SB, the entropy at point A minus entropy at point B is equal or greater than the change of B to A, and that is del Q by T. So entropy change from A to B is greater than this del Q by T term. Okay. And if it is reversible, it will be equal. So let me write first the reversible case. If that cycle is totally reversible. So it means that it is from A to B as well as B to A. Okay. Therefore, for that case, if it is totally reversible, I can write this one as SA minus SP, and this term will be SA minus SP, and this will be equal if it is totally reversible. But if one case is the irreversible path, you will not have this equality, you will have that inequality greater than that term. Okay, and this is the first stuff. It is only for reversible, totally reversible. This part is reversible, that part is reversible. And for the general case, this term is greater than that one. So what I will do is that I say that SA minus SP will be equal to that from B to A and del Q by T plus some generation. Okay, and this is the term that we are interested in, the equation. And entropy difference between A and the B is equal to the integral of del Q by T from B to A plus the generation. And this generation is always positive. Okay? And the minimum case is that it is 0. It is equal to 0. And that is equal to 0 when it is totally reversible process. But when it is the general process, it is always positive quantity. And this quantity is called the entropy generation. So it is that creation, it is, I think, the better term to understand what it means of entropy. So it means that when you travel from A to B, and in that case, the entropy from A to B, this one increases. Okay, the term from A to B, entropy change, it is not the equal that the difference between that A entropy minus B entropy, but plus some additional positive term. Okay, so it means that during that process, when you travel from A to B, and there is some positive quantity that is dumped into your path, and that positive quantity, so in the next slides you will see that that positive quantity, which is generation part, it makes the process irreversible. You cannot travel back. So that process becomes irreversible. It can be the source of this generation term. Since it is irreversible, we have talked about this one, it can be friction, or it can be that delta T temperature difference finite, or the force difference, and it can be that delta P, any finite gradient that will create the generation of the entropy. But if it is reversible, there will not be a generation term. Okay, so if it is totally reversible, then you will have SA minus SP, the difference between entropy A to B, and that one will be the same as that if you travel in that manner, or if you travel in that way, it doesn't matter, the entropy change is fixed. Okay, now I will talk about the diagrams and the entropy change of pure substances, which is the second part of it. So that we have also very similar to the TNU diagram, for example, for water. This is the TNU diagram of it. And we have also TS diagram, the temperature versus entropy. And we have also HS diagram, which is the enthalpy versus entropy. Okay, we have the different diagrams, and these are all for water. Okay, and this one shows how temperature changes with respect to entropy at different constant values of the pressure. And this one shows how that enthalpy changes with respect to entropy and with different values of the pressure. And for the first one, you have the 100 kilopascal, then you have 620 and 2000 and 500, sorry, 200 and these 11,000 kilopascals. Okay, and with different pressure values, this one shows the variation of temperature with respect to entropy. This one shows the variation of temperature with respect to specific volume, and it is for water. Similarly, we have relationships for air, and you have the temperature change with respect to entropy at different values of the pressure. Similarly, enthalpy with respect to entropy. So what it shows is that there is a relation between temperature and entropy. There is a relationship between enthalpy and the entropy. And we have the relationship between the temperature and entropy for water as well. And this is the first stuff. So this one shows that relationship or formula, we can say. There is a formula between T and S, or H and S, etc. And the second one is that this one says that you can use the things that we have done for the pure substances. So we can use, for example, that quality. This is the famous one for entropy as well. Or you can use that SF, or you can use SG, which are from thermodynamics one. These are the two important results from the chart. Okay, now will come the first equation of the semester for a closed system, which will be an important equation. So firstly, let me show the closed system here. And this one is always piston cylinder device. This piston cylinder device has some pure substance inside it. It can expand or it can compress, but let's look at a case where it expands. Okay. And therefore you will have that heat transfer into that system, Q in, and you will have the work done by the system, which is the work out, and the change of that is internal energy of the system. Okay, now let's write that one, so that du will be equal to that del Q in minus del work out. Okay. And this one is, we are looking for internal reversible process. For this internal reversible process, if you remember, we have said that del Q by T is that ds. So therefore del Q will be and the T ds. That's the first. And also we have this term which is del work out. I can write this one as that PdV or PD nu. And therefore what you will have as a result is that du, and this one is also lowercase to make the quantities per unit mass, but mass can change. And if there is mass, you can cancel out from all of the terms. It doesn't matter here. And the du will be equal to and the TdS minus PD nu. Okay. And this final result says that this one shows the relation between point functions. Okay. And however, we started with internal reversible process. The final result, the du and the TdS and the PD nu, it doesn't depend on the path. You can see that the final result is independent on the path. So that means that it is true for, since it is independent of the path, and it is true for, it is reversible or irreversible. At the end, it shows that is relation between the point functions, change in properties. Okay? Therefore, true for that irreversible or reversible, doesn't matter. It doesn't matter whether it is reversible or it is irreversible. This relationship is always true. And this is the first one. And the second relationship that I'm going to use is that now I will convert these quantities into the enthalpy relationships. And if you remember that enthalpy is that d into u plus p nu. Okay. And instead of that one, you can write d nu plus PD nu and plus nu dp. For this relationship here, I will do that replacement here. du will be PD nu, and that one will be equal to TdS. And I will replace this one here. It will be that dH minus nu dp is equal to that TdS. Or that the second equation will be that dH will be equal to TdS plus nu dp. That one is the second equation. The first equation is that du is TdS minus PD nu, and the dH is TdS minus nu dp. And for the first equation, and this one is the second important equation. But I can write these equations in terms of the entropy difference, and the entropy difference is equal to du by T minus PD nu by T. This is the first one. And the second one is that entropy is at dH by T and plus nu dp by T. This one is the second. And by using these two relationships, we will generate that, we will look for the entropy change for pure substances in our next slides. and this one we can say that this is 1A, and this one is that 2A, because we have derived these relationships from these equations here. Okay, I have a small error here, but this one will be minus nu dp by t. We will use these equations for the change of the pure substances, as I stated. This is the first equation. Equation, if it comes in the picture, the first one. Or this, okay, so this is the second one, the equation that we have got here. And also you have the equation for the du by t minus p nu by t. Okay. Entropy change of incompressible substances. Let's look at this one. So I will say that T ds is equal to du by t minus p d nu by. For the incompressible substances, we have the d nu is equal to 0. The volume doesn't change, or you can write this one as dv by m, and that one is equal to 0. For incompressible substances, we don't have any change in volume, okay, per unit mass. Therefore, this quantity is 0. And also, you can write that instead of du, you can write Cv dt. Therefore, ds will be equal to Cv into dt divided by t. Okay, and to find the entropy relationships between 1 and 2, okay, and you will have that delta S or S2 minus S1. Okay, now what will I do is that to be able to integrate this one, to assume that Cv is constant. And if you assume that Cv is constant, then you will have that Cv and ln T2 by T1. Okay. This one will be Cv average. This is the entropy relationship for the incompressible substances. For incompressible substances, entropy change is equal to Cv average ln T2 by T1. Okay. And entropy change of the ideal gases, now let's see that one too. And we have said that, let's go back to the first slide. For incompressible substances, we can use the formula that we have derived. Okay. That formula was del Sy is equal to Cv ln T2 by T1. Or you can use the table, or you can use any software. This one is easy, but you can use any software to find the entropy change. And the table is you can see the tables for the superheated, saturated water tables. Now comes the ideal gas formulas. Now let's see that one too. So we have two equations. I will write the equations here. So the first equation is that ds is du by t minus p nu by t. This is the first relationship. And the second relationship is that ds is dh by t minus nu dp by t. This is the second relationship. And now let's use for the ideal gases. And for ideal gases, you can write this one du as will be Cv dt. Okay, and the p nu is RT. And therefore, instead of P, you can write RT by nu. Okay, now let's replace it. I will work in two parts here. Let's replace it, and you will have that ds is equal to that Cv dt, and divide by the temperature minus, and you will have RT by nu instead of P multiplied by du by t. And t cancels out. And you will integrate as always from 1 to 2, this one from 1 to 2, and this one from 1 to 2, and this one from 1 to 2. Okay, now we will assume that again that Cv is constant. Okay, that we will assume that constant Cv. For that constant Cv, you will have that del S is equal to that Cv average and ln T2 by T1 minus that you will have R into ln nu2 by nu1. Okay, this is the entropy change for the ideal gases. But we have assumed that Cv is constant. Now let's see the second case. Let's see. This one doesn't give a different relationship, but at the end, it is different manifestation of the first law. you have replaced du with dh, you will have that similar relationship, but instead of Cv, you will have Cp. Now let's do that, and the dh will be equal to Cp dt. And therefore, ds will be equal to Cp dt and divide by t minus, and instead of nu dp, I will write similarly here. And so let me show all the steps here. So p nu is RT, and the nu will be that RT by P. And it will be that RT by pressure and dP by temperature. Temperature cancels out, and I will integrate now that quantities from any point of 1 to 2, any point of 1 to 2, any point of 1 to 2. And here I will assume that Cp is constant. Okay. Again, this is an approximation, and you will have that del S is equal to Cp ln T2 by T1 minus that second part will be R multiplied with ln P2 by P1. Okay. This is the second. Let me see if I have any errors here. No, okay, it seems okay. This is the second relationship. But if you go back to the first part here, for ideal gases, we have constant Cp/Cv part, and we use only formula. But if it is variable, we have half formula, we have the table, and we have the x. Okay. Now let's look at the variable Cp/Cv case now. We will use that table, and the table is only prepared for that Cp formula. So variable Cp. Okay. And for that variable Cp, if you see that formula here, Cp and the dt by t. Here, for ideal gases, I should note it that Cv and the Cp are functions of temperature. Okay. They are different functions of the temperature, but generally I'll show it as Ft. To integrate that quantity, what people have done is that the Cp dt has been evaluated from 0 to some temperature T. Let's say the T1. And that is shown as S sub S super 0. Okay. And this one has been, that has been calculated. Okay, they have calculated this one, and also they have tabulated. And this value is shown in the tables. And therefore, S02 minus S01 will be equal to, if you subtract these two quantities, it will be 0 to T2, first one, of Cp and the dt by temperature, minus, for the second one, from 0 to T1 Cp dt by T. Okay, this is for the second one. Okay. Now for the integral rules, if you remember it, it will be that 0 to T2 of Cp dt by temperature. I can add it. It will be that T1 to 0 and Cp dt by T. That is exactly equal to from T1 to T2 by the rules of the integral and Cp dt by T. And the T1 by T2, this is the integral that I am trying to do. Let me add it here. So you will have that ds from 1 to 2, it will be equal to Cp and the dt by temperature from 1 to 2, and this one minus RT by pressure and the dP by temperature from 1 to 2. For the first part, it is easy. This one is del S. For the second part, I will keep it. For the third part, it is also easy. It will be that R ln P2 by P1. These ones are exact. And for the second one, this is also exact, but it is tabulated. From T1 to 2, it is Cp dt by T. You can see it is the same one here. That one will be the difference of these two quantities here. Okay. And the formula will say that S2 sub 0 minus S1 sub 0 minus R super 0, ln P2 by P1. Okay. These two quantities are in the tables. We will do examples for these ones. If you look at the tables, you can see these two formulas there. Okay, let me go back to the case here. So I've done the incompressible substances, finished it, ideal gases, constant Cp/Cv, finished, and the variable Cp/Cv. This one was the half formula, and that half formula was saying that S2 minus S1 was equal to S2 0. This is half formula because for this one you use table, and minus R ln P2 by P1. and the general formulas, the tables you can use it, and the ease. And for the constant CP/CV, you have two different del S, and the one is with CV and the other one is with CP. We have finished that part. I have finished this part. Now comes the non-conservation of entropy. Let's see that one. The non-conservation of entropy. And we will first start with the energy balance and then the entropy balance. So for any general balance, you have the change of property, which is equal to in minus out plus generated terms plus the destroyed terms. If it is energy, then these two terms are zero. Therefore, the change of total energy of the system will be internal energy, potential energy, and the kinetic energy. It will be equal to in minus out. Okay. And if it is rate quantities, it will be divided by del T and divide by delta T and divide by delta T. You will add the dots here. The energy transfer can happen in three ways. One is that heat, the other one is work, and the third one is mass. And mass can carry with itself enthalpy, it can carry kinetic energy, it can carry potential energy. This is for the energy balance. And for this system here, or for this system here, okay, for this system here, we can write this energy balance here. And these are the same systems. So I will have that change of internal energy, potential energy, and the kinetic energy of the system. Generally, change of energy of the system. It will be equal to, you can see there is work out, there is work in, Q dot out, this one is out. And there is also mass transfer. This mass carries the enthalpy, kinetic energy, and the potential energy. Okay, so if I write it, dE by dt will be equal to that m dot into h, kinetic energy plus potential energy. These are ins plus q dot, that is in, and plus work dot, that is in. This is q dot and this is work dot, minus. So you will have that m dot h plus kinetic energy plus potential energy. This one is out part, minus. So sorry, q dot out plus work dot out, and the sum of it. This is the energy balance. Now what happens if we try the non-conservation of entropy? For the non-conservation of the entropy, it will be a bit different. Now let's see it. The first thing is that for non-conservation of entropy is that there is no destroyed term. This is the zero for entropy. That is very same as that is energy. But the generated term is there. Entropy is generated. Okay. And now let's write this one as the entropy now. We'll have that change of property is entropy. So it will be, I'm gonna write this one as entropy. Change of entropy will be equal to that in minus, this one is a closed system. Let me write it here. So change of entropy del S will be equal to in del S by del T time minus out. We can write it as rate quantities, or we can write in joule units, even joule by kilograms units. Del S by T, it will be in minus out. And for the difference between entropy and the energy, is the first thing is that there is generation, it's okay. And the second thing is that for entropy, you have the entropy transfer by heat, you have the entropy transfer by mass, but there is no entropy transfer by work. Okay, work doesn't carry entropy with itself. Okay, that is the first important difference between the energy conservation and the non-conservation of the entropy. And entropy transfer by heat, it is shown as Q dot by the temperature. Or if you are looking for the integral terms, it will be that del Q by the temperature with the rate quantity. For the entropy transfer by the mass, you can write that mass multiplied with entropy. If it is inlet, it will be that mass transfer multiplied with enthalpy inlet. If it is outlet, mass transfer times enthalpy outlet. And for the temperature here, the T value, it is very important temperature, and it is the boundary temperature where you have the transfer of the heat. For the problem here, you can see the boundary temperature is fixed everywhere. Therefore, all of the heat transfers happen from this boundary where you have that T boundary. And also this Q dot in is constant and Q dot out is constant. Therefore, there is no need to take this integral part here. You can write this general term. And with that case, you will have that del S by delta T of the system will be equal to in, which is that Q dot in divided by that boundary temperature. Here the boundary is the same everywhere, so it will be that TB, okay, also for in quantity here, and plus that mass transfer. There is mass into the system and it carries entropy with itself. These are for inlets, and minus the out parts. You will have that similar relationship here, Q dot out, that is divided by this boundary temperature here, TB out, okay, divided by that TB out plus m dot S out. Okay, this is for the open systems. Okay, this is for the open systems. You have the entropy transfer into the system, entropy transfer out of the system, and change of the entropy of the system, which is del S by del T of the system. For the problem here, the boundary temperature is same everywhere, therefore you can replace this one as the TB above. Now what happens if it is that one is closed system? This one is closed. For that closed system, the energy transfer, first the conservation of energy, it will be that dE by dt of the system will be equal to that Q dot in plus work dot in minus Q dot out plus work dot out. This is for the energy. And for the entropy, so I forgot to add one thing here, is that you have that generation. I should add the generation part here, rate. If this is generated entropy. Okay, so for the entropy, you will have that change of entropy for a closed system. This one is for the system. Here it is that dE by dt of the system, and here you have that del S by del T of the system. Similarly, here you can write it also to del S by delta T of the system. And this one will be equal to, there is no mass transfer, therefore it's only heat with TB here. There is only heat and with TB here. So you will have that is Q dot in divided by that TB in, this is for inlet, minus Q dot out and divided by TB out, this is for outlet, and plus the generation part with rate, entropy generation. Okay, this is for the closed systems. Okay, you can say this is for closed system, this is for open system, always generation. For energy, there is no generation, there is no mass, there is no mass, there is generation, there is no generation. Okay, now what happens if there is no heat transfer, if there is no mass transfer? Let's see that one. In that case, for the energy, dE by dt, there is no heat transfer, there is no mass transfer, therefore this term is 0. Okay, and the dE of the dt of the system is 0. So in other words, E is constant with respect to time. It doesn't change. Now let's see the entropy case. The heat is 0, this heat is 0, and therefore the change of entropy of the system is equal to generation. Okay, you can see for energy it is 0, but for entropy it is equal to generation. It is like a production facility. You are always producing, you are always producing. For this one it is 0, but this one is always producing new entropy, new entropy, new entropy. It is like the inflation of money in a poor economy. The money is always inflating, always inflating. Okay. Now let's take so this one is our isolated systems. This one is isolated, this one is closed, and this one is open. And let's take our universe. Our universe, if you take the boundaries so that it is isolated. Okay. And for our universe, energy is constant. It doesn't increase or decrease what it says. But entropy is positive. the change of entropy with respect to time is always positive. And when it can be 0, del S by del T is 0 when it is reversible. For reversible processes, this term is 0, no generation. But since the universe is not reversible, it is irreversible, therefore this is always greater than 0. Del S by del T is always greater than 0 for the universe. Okay, isentropic processes, now we have said it, it should be reversible and it should be adiabatic. In that case, S1 is same as S2 or delta S is equal to 0. Okay, now, firstly, I will look for the isentropic processes for which is incompressible substances. For incompressible substances, if you remember the formula, it was S2 minus S1 CV average ln T2 by T1. So that S2 minus S1 will be equal to CV average and ln T2 by T1. Okay. And if it is isentropic, the term here is 0, and therefore ln T2 by T1 is 0, or T1 is equal to T2. If it is incompressible substance, isentropic means that temperatures are the same. Now comes the ideal gases. For ideal gases, I have two relationships. One is for CV and one is for CP. Now let's first write that CV value here. The delta S will be equal to CV average. We'll have ln T2 by T1 minus R times ln nu2 by nu1. Okay. Let me go back to here. We'll have that Cp ln T2 by T1 R ln P2 by P1. So you will have that del S Cp average, and ln you will have again T2 by T1 minus R ln P2 by P1. This is the second one, and you have three formulas. The last one says that you will have that del S is equal to, and this one you will have that del S is equal to S2, not on it S1, not on it minus R ln P2 by P1. Now let's see the first case. If the entropy is constant, the left hand side will be 0. You will have that CV average. You will have ln T2 by T1 will be equal to R ln nu2 by nu1. Okay. Now I will write the terms here as, let me take brackets so that they are not mixed. And for the one that is here, I will write this one as, and you will have that ln, instead of CV average, I can just write this one as CV, but it means that CV average ln, and you will have that T2 by T1 will be equal to R by CV and ln nu2 by nu1. And you know that we can get to the power nu2 by nu1 and to the power of R by CV. I'm getting this one to the power of ln. If you exponentiate both sides, you will have that T2 by T1 will be equal to nu2 by nu1 to the power of R by CV. Or you can get that instead of R, for ideal gases, if you remember that R is Cp minus Cv. For the ideal gases, R is Cp minus Cv, and you can just replace it there. You will have that Cp minus Cv divided by Cv, and that one will be equal to Cp divided by Cv minus 1. That one will be equal to K minus 1, and the nu2 by nu1 to the power of K minus 1. That is. Now let's look at the isentropic relationships for the second one here. You will have that del S will be equal to, instead of Cp average, I will just write the Cp and ln T2 by T1 minus R ln P2 by P1. Again, it is isentropic. The left hand side is 0. You will have that T2 by T1 will be equal to P2 by P1, and to the power of that one will be R by Cp. And for R by Cv, we have written it, and let's solve for R by Cp's. Again, that Cp minus Cv divided by Cp. That one will be 1 minus 1 divided by K. Yeah, so it will be that instead of that one, you will write this quantity here. These are for the ideal gases and for the second relationship. And for the third relationship, you will have that del S will be equal to St0 minus S10 and minus R in the multiplied with ln P2 by P1. And if the left-hand side is 0 because it is isentropic, you will have that S2 sub 0, S2 super 0 minus S1 super 0. It will be that R ln P2 by P1. Okay. And then you can do this quantity like P2 by P1. It will be equal to S2 to the power of 0, S1 to the power of 0. You will have that is ln here. And S divided by R. And therefore you can say that P2 by P1 will be equal to e to the power of S2 super 0 divided by R and minus S1 super 0. Using the function of the exponential one, you can say that S2 super 0 divided by R and E S1 super 0 divided by R. And these two quantities has been evaluated in the chart, and this one has been evaluated as PR2, and this one has been evaluated as PR1. And this one is equal to PR2 divided by PR1. These are all in tables. Okay. And this is called the reduced pressure. And the reduced pressure PR is e to the power of S2 to the power of 0 divided by R. Okay, exponential. This has been evaluated in the tables, and you can look at the tables and find the related values. Okay, so I have shown the isentropic processes for the ideal gas, for the incompressible substances, and for the ideal gases variation of the Cp and the Cv. We can also play with ideal gas relationships, and instead of P2 by P1, you can just write that nu2 and the nu1 relationships by working out these ones, and you can get a different relationship, and you will get that nu2 by nu1 will be equal to nu r2 by nu r1. Okay. This is also in the tables, and it is reduced volume. You can just replace it to the initial form here because it is R ln P2 by P1, and instead of that one, what you can do is that you can write at RT2 by nu2. This one will be that RT1 by nu1. And we will go back to the initial forms of the equations, and we will just replace nu2 by nu1, and the rest is calculated as the reduced volume in the table. So we'll derive the Bernoulli's equation for by using equations that we have derived for the entropy, and I will take an open system here. This one is open system. You have the outlet, you have the inlet. Okay. And this one is the outlet. You can also have that work and the heat transfer. Now I will just write that is conservation of energy. And what I will assume here is that for conservation of energy, that there are Bernoulli's approximations. I will just write the first approximation, which is steady. I will add the approximations, and this one is the 1, and this one is the 2. Okay, and you will have that enthalpy at 1 plus kinetic energy at 1 plus the potential energy at 1, and plus, if it is Q in, you can add that Q in. Okay, and that one will be equal to that enthalpy at 2 plus kinetic energy at 2 and plus potential energy at 2, and plus you will have that del work out, okay, out of the system. Second assumption of the Bernoulli's principle is that so it is there cannot be any work producing or work consuming device. Work producing or consuming device. Therefore, the term here goes away. And I will go to the differential definitions, and therefore that Q in it will be equal to H2 minus H1 and plus kinetic energy 2 minus kinetic energy 1 and plus potential energy 2 minus potential energy 1. For the differential terms, it will be del Q in will be equal to that dH plus that d kinetic energy plus that d potential energy. And instead of that del Q in, so that Bernoulli's principle is for reversible processes. Okay. And then instead of that one, I can write TdS will be equal to dH plus d kinetic energy plus d potential energy. That is for the Bernoulli's principle. That's for the Bernoulli's principle. Now what I will do is that I will use these dH relationships that we have derived, so that remember dH was TdS plus nu dP. This one was TdS plus nu dP, so it will be that equal to TdS plus nu dP plus d kinetic energy and plus d potential energy. These two terms cancel out. You will have that nu dP plus that d kinetic energy and plus d potential energy is equal to 0. And then what you can do is that you can integrate the quantities here, integrate it and integrate it from 1 to 2, from 1 to 2, and from 1 to 2. And the next approximation for the Bernoulli's principle is fourth one, it is incompressible. Okay, therefore nu is constant. Nu will get out of the brackets. You will have that P2 minus P1 plus kinetic energy 2 minus kinetic energy 1 plus potential energy 2 minus potential energy 1. And therefore P2 by rho plus kinetic energy 2 plus potential energy 2 is same as P1 by rho plus kinetic energy 1 plus potential energy 1. We have seen that we have derived the Bernoulli's result from the entropy relationships with using these four approximations: steady, reversible, incompressible, and no work or producing or consuming device. Now comes the isentropic efficiencies. Now we are going to talk about isentropic efficiency of the turbine. Then we will talk about the compressor, then the nozzle. And for the turbine, let's start from the turbine. So what the turbine is that it uses energy of a fluid. Say that I have a fluid that enters into that system with the T1 and the P1. And this is T1 and P1. Okay. And we can get the maximum work from this turbine if it is reversible and adiabatic. We can get it by, if it is reversible adiabatic, then entropies are the same. This will be the maximum work that we can get. The entropy remains constant. And in that case, the outlet value of this one, let's say that it is P2. Okay. If it is isentropic, then outlet is fixed by entropy. Entropy at state 2, which is equal to entropy at state 1, as well as the pressure at 2. Okay, therefore this is the for the isentropic case. So for the reversible one and the adiabatic one, you will have this process, and you will have T1, P1, and then you will have that P2, T2, or S2. But this S2 is same as S1 here. This is for the isentropic work. So if you write the first law for the turbine, the first law will dictate that work done by the turbine will be equal to, if it is isentropic case, the maximum one, it will be that H2 isentropic minus H1. And the H2 isentropic means that H2 you can find by using that entropy and pressure, or you can use entropy or temperature, etc. Any two properties, but one is entropy, where that entropy 2 is same as entropy 1. This is for isentropic work. But for real work, let me use different color here, so that work out real. It will be just H2 minus H1. Okay. For the real, that is turbine work. For the real one, the entropy will increase, may go in that way. You can see that this is the real one. You are at the same outlet, which is P2, but you are at a different temperature, T2, and a different entropy. This is the real one. And as we know that on isentropic one will have more efficiency, therefore that eta will be equal to H2 minus H1, the real one, divided by H2 isentropic minus H1. This is the isentropic efficiency for the turbine. You are at the same outlet values, which is the P2. You are at the same outlet values for the first one, which is P2. But the work done is different. Okay? Because in the first case, S2 is same as S1, but here S2 is not the same as S1. You should remember that P2 isentropic turbine is same as P2 real turbine. You are doing the work between two same pressure gradients. But in one case it is isentropic, in one case it is not isentropic. And similarly here, if it is isentropic, for example, we are doing work in that way, it will be some perpendicular line. It will be from H1 to H2. If it is in that way, if it is a real one, it will be in that way. Entropy will increase. Will be H2 real. Sorry, H1, H2 isentropic. You can notice from here that this real one will do this amount of work. You can see that amount of work. This one is the work by real, but isentropic one will do that amount of work. Okay. That is the difference between the isentropic work and the real work. Now for the turbine, so for the compressor now, this one is the compressor. I will compress it from P1 to P2 again. But now I will first case it will be isentropic, where you have the same pressure differences, but now isentropic. This one is isentropic. For the real one, it will be an entropy increase. You can see you have the same pressure differences, but in one way it will be isentropic path, and here it is real one. And if you look at the enthalpy diagram here, so in the isentropic case, it will be vertical up, but in the real case, it will be something like this one. This one is isentropic and this one is real. Now you can notice the differences here. For the isentropic one, you will need less amount of work. You can see this is the work for isentropic. Okay, you will need less amount of work for isentropic one. Use different color here. But for the real one, you can see the amount of the work that is required. So it means that compressor will need more work for the real one. Why? The reason is that because you have friction, you have the heat transfer losses, and this friction and heat losses from the system require more work, because some of the work is spent on the friction to overcome the friction. Therefore, you will need more electricity to drive that compressor. And for these reasons, that isentropic efficiency of the compressor will be, so that it will be H2 minus H1, but H2 isentropic minus H1, to make it between 0 and 1. Otherwise, it will be greater than 1. But here, you can see it is less. This one is small, and this one is large. Okay. Therefore, you divide in the opposite sense, and you get the isentropic relationship for the compressor. Okay, now let's look at the nozzle here. We have the nozzle. Again, nozzle change the pressure from P1 to a P2 value here. Okay. And since the velocity increases, P2 is less than P1. Okay. From P1 to P2, first we'll take the isentropic path, and second we will take the real one. For the isentropic one, what you'll have is that h1 plus v1 squared by 2 will be equal to h2 isentropic, and the velocity 2, which will be isentropic 2. Because if it is isentropic, the velocity will be different than the real one, and therefore we put isentropic subscript here. If it is real, we will have that h1 v1 squared by 2 will be equal to h2, and here you don't have any subscript, so you will have h2 plus v2 squared by 2. This one is for the real one. Now we are trying to determine in which case the enthalpy difference is larger, isentropic one or the real one. Now let's look at the chart. For the real one, this is the real one, you can see that entropy, for the isentropic one, the entropy is constant. I'm traveling in between two states. So this one is the isentropic. And similarly here. This one is del H isentropic, between the same pressure units. But if I go to the same unit with the isentropic, so the real one, this one is the real one, entropy increases, and in that case, that enthalpy difference here, del H real. You can see that del H real is less than del H isentropic for the nozzle, and therefore that nozzle entropy efficiency will be equal to, so H2 minus H1 real one divided by H2 isentropic minus H1. Okay, to reach the same pressure difference. Okay, the reason is that for the real one you have friction. Okay, that friction adds energy to enthalpy. Okay, therefore enthalpy at outlet due to friction is more, because you have friction, it means temperature, temperature means enthalpy. Therefore at outlet for the real one, due to amount of the friction, you have more enthalpy. You can see. But for the isentropic one, there is no friction, and therefore that enthalpy at the outlet is small. This one is for isentropic one, and this one is for the real one. You can see the differences in enthalpy. This one is added, there is an added amount of energy at outlet due to friction. Friction adds energy to enthalpy since it is heat. Okay, and the h1 by plus v1 squared by 2 is the same for all cases. Okay, it is same here and it is same here. Therefore, if you write the right hand side balances, you will have that h2 isentropic plus v2 isentropic squared by 2 will be equal to h2 plus v2 squared by 2. And since h2 real one, so let me do that, h2 real one is greater than h2 isentropic one, that one is greater. Since these two are equal, it means that v2 should be less than v2 isentropic. That is also very clear, because due to friction, this one decreases velocity 2. This one decreases velocity 2, but since there is no friction, the velocity is high. Here you have high velocity, a low enthalpy at outlet. Here you have the low velocity, high enthalpy due to friction. Okay. These are the isentropic efficiencies of the devices. So I have finished this part, I have finished that one, I have finished this one. Okay, and for the pumps, I have forgot to add it that it is the same as the compressor. It is not different, same. For the pump here, they are doing the similar works. One works for the gases, one works for the incompressible substances. The difference is the same. Okay, now comes the last part, which is the definition of entropy. There are different definitions of the entropy. If you look at the internet, Google it, you can see that there are large definitions for the entropy. And it is like, you know, you are looking at a big picture from which side. That there is a big picture in front of you, and you are trying to imagine what happens in that great picture. So if you see a small block of it, you are trying to build the general picture from that block. or it is like the map of the world. We're trying to understand the map of the world from a part. Okay, now comes the definition of the entropy. Okay, there are different definitions for the entropy, and there is no one fixed entropy definition that we can say this is it. There are different, for example, for second law, you can see that there is Kelvin-Planck statement, there is Clausius statement, there are also other statements, and also there is statistical definition for entropy. I will show some common definitions for entropy, but you should keep in mind that it is not one simple definition. It is like there is a large picture in front of it, and you are seeing only a part of that picture. And from that small part of that picture, you are trying to understand what is the general picture. Okay? What happens in the general picture, and you are trying to get it from that small part of it. Entropy is like that one. It is a large concept, and we are trying to understand that large concept from simple definitions. Therefore, there is not a general agreed definition for the entropy. And one definition is that the irreversibility, we have covered this one, which is macroscopic definition, which is the easiest one. And this easiest definition says that if you are traveling from A to B, okay, and from that travel from A to B, there is entropy change, which is SA minus SP. Okay. That is not enough. There is also that entropy generation. During that process, entropy is generated. It is like the inflation of money. You have some $100. At the end, you are expecting to be $200 due to your salary, but it is not $200. It is more than that one due to inflation. Okay, that is the definition of the entropy. And that inflation amount is not constant. It depends with respect to country. And entropy also, it is not, generation is not constant. It depends on the type of the process. It can be more entropy generation. It can be less entropy generation. It can be in ideal conditions, 0. This is the people that see 85% full of this glass. And there are people that see also 15% of the glass, which says that entropy is the measure of energy dispersal. I say that at the beginning you have this amount of energy which is compact. From this compact amount of energy you are trying to get some work. Now the amount of the work is in that space, and from this space you have different amount of energies. Now you have the kinetic energy, you have potential energy, you have the internal energy. From these different types of energies you are trying to get work again. It is very difficult to get high quality energy. And now another definition is that measure of uncertainty. Okay, that measure of uncertainty means that, so you have a system here. This one is the statistical definition. It's better to statistical definition, or it is about also information theory. What it says is that as the process happens, so at the beginning of the process, we had more information about the configuration of the atoms or molecules, their microstates. But as the process happens, we are losing information about the microstates of the system. As the process happens, molecules takes a space that increases our uncertainty about that system. Okay. That measure of uncertainty that we are achieving during that process is called entropy. Okay, one last definition of the entropy is the disorder, and in that definition of the entropy, it is also under discussion. Okay, the people say that it is not the true and that it doesn't convey the real meaning of the entropy, etc. But there is also a chapter from the Chengiz book that discusses the disorder concept in entropy, and the last definition of the entropy is that it measures the disorder of the system. Okay, it is like, you know, that if you are tidy, your books are, you can find your books in the shelf. If you are tidy, you can say that this is book 1, this is the chapter 2, this is another book, if you are tidy. But if you are not enough tidy, and then your books will be in different shelves and different states, and it is not possible to determine where the book is. For example, the thermodynamics book is, where the fluid mechanics book is, in which shelf. this is the disorder that we are talking about the definition of the entropy. And as I said, this one is under discussion. And okay, there are the other definitions for the entropy, but I like the best one, which is the irreversibility or the macroscopic one. This one says that during the process, this is very simple as it is, and it's also the classical definition, classical thermodynamic definition. During the process, we have that new creation of property. That new creation of property is entropy, and that property, that stops the reversibility of the process. The process cannot reverse itself again. Okay, so with this one, I finish the entropy chapter theory, and then we'll have examples about the entropy.